A very warm welcome, everyone, to the Maritime Education Podcast. My name is Barry Sadler, and after another rather windy and wet evening, I'd like to talk to you today a little bit about weather forecasting and the effect that it can have on ship handling and pilotage in general. Last night saw perhaps the start of our winter season of winds. 30th of August 2025, and we've seen a rather intense low pressure pass across the United Kingdom. This was the second weekend in a row that saw the pressure drop around the British Isles and the storm come through, bringing with it winds in excess of 30 knots and reminding us that the good old southwester is just a few weeks away from being a regular thing here in the UK as we transition from summer into, of course, the fall and into winter. The prediction of these storms coming across is particularly difficult at this time of year. The chaotic weather events that happen high up in the atmosphere during the summer, due to the amount of heat released from the Earth's surface, can make forecasting particularly difficult. And at times the forecasts that we receive as pilots can be out by a considerable amount. Now, when we say out by a considerable amount, we're probably talking 5 or 10 knots either way. But last night the wind was actually a little bit more powerful than it was forecast to be. The forecast yesterday was for 40 knot winds at the pilot boarding station in Southampton. Now, 40 knots of wind is going to generate some significant wind and swell waves in the vicinity of the pilot station, and it's going to make boarding and landing of ships particularly challenging. And therefore, when we have a 40 knot wind forecast, we are obviously increasing our awareness of the weather. We're putting in place measures to ensure that as conditions deteriorate, we manage the risk accordingly, and if necessary, we either adjust the boarding time of ships, or we abort ships, or we try and position ships in a more favourable place to board them in the specific weather conditions that we're experiencing. The forecast at the notorious NAB pilot station last night was for 40 knots of wind, and as the wind started to increase in the early evening, it was evident that we were going to get a little bit more than that. In fact, the wind gusts out at the NAB tower weren't 40 knots, but we did have a gust of 51 knots at some point. Now, this generated extra seas and swells out at the NAB tower and caused us to shut the pilot station earlier than anticipated. In fact, we didn't even anticipate having to shut the pilot station based upon the forecast, but with the wind increasing beyond the forecast levels and generating dangerously high swells and sea waves, the decision was taken to close the pilot station at around 8 o'clock last night, and it didn't reopen fully until around 2:30 in the morning. So it's a 6.5 hour closure of the pilot station. Now, closing the pilot station is something that we can do in advance if we know the weather forecast is going to be bad, and of course by observing the increase in winds carefully, we can of course close the pilot station in reaction to the actual conditions that we see forecast. If we look at the other end of the pilotage, i.e. we've got on board the ship, the other end of the pilotage berthing the ship, then an increase in wind of 10 knots beyond that forecast can have a real effect on the ship handling, and in particular on the amount of tugs that we use to handle our ships on and off the berth. Now, a good example of this is if we consider one of our biggest container ships that uses the port of Southampton. The Busan Express and the Hamburg Express are two very, very large vessels that use the port, and they do have huge windage on the side. Now, I'm using these two ships as examples because we know exactly what the windage is, particularly of the Busan Express, because I have the calculations to hand. Those express boats are on a different loop now, but we are still seeing Category 7 container ships coming into Southampton with very, very similar windages. Now, the windage on the side of one of these massive container ships is somewhere in the region of between 16 and 18,000 metres squared. Now, in the case of our Busan Express, the wind force at 40 knots is 384 tons. So in other words, 40 knots of wind on the side of the ship is able to exert that lateral pressure. So as a ship handler, we need to make sure that, scientifically speaking, we have at least 384 tons of thrust and tugs to be able to meet that wind and therefore be able to control the advance of the ship towards the berth. Now, if we say that the wind speed increases by 10 knots, that actually increases the lateral wind force by around 86 tons. Now, this is quite significant in itself because 86 tons is slightly bigger than the size of a tug. So in other words, if we had planned on, let's say, 3 tugs for berthing the vessel at 40 knots of wind, and we end up with 50 knots of wind, that would indicate that mathematically we needed 4 tugs. And that's something that as a pilot we would go through with the master when trying to justify taking extra tugs. But if the forecast is a lot lower than the actual wind speed that we experience, it may be that we haven't had that discussion, we haven't taken that tug, and therefore obviously can get caught out if we're not extremely careful. Now, obviously the experience of the pilot, sometimes we can see that the wind is shaping up to be slightly stronger than that's forecast, and we can act accordingly as an experienced pilot and ensure that we put in place the measures necessary to meet those extra few knots of wind. But let's talk about weather forecasting, because we're now at a stage where artificial intelligence is being used on a daily basis to make these weather forecasting predictions, and therefore 10 extra knots as there was last night at the NAB Tower is a significant difference in the forecast compared to the actual wind speeds that we experienced. Now let's go back, shall we, to pre-scientific meteorology. So let's go back, if you like, to pre-16th century and talk about how people used to interpret the weather. A lot of weather in those days, before meteorological science was born, was based upon folklore. Now, folklore still exists today, and a lot of people talk about several things that you can observe in the skies that are going to indicate that you're going to have either good or very, very poor weather. One of the most popular ones of those is, of course, red sky at night, sailor's delight, red sky in the morning, sailor's warning. Meaning that if we do get a red sky at night, that indicates that the following 12 hours are going to be fairly nice weather. Whereas if we get a red sky in the morning, it's quite the opposite, that we are going to get deteriorating weather conditions. This is all about, of course, the sun shining through the upper atmosphere as it rises and sets, and the direction at which the sun is actually shining will indicate where the dodgy weather is. So if the sun rises in the east and it's shining red, then it's indicating that the dodgy weather is coming in from the west. Therefore, it's going to get to us. And vice versa, if it's red sky at night, then it's reflecting off weather that has already passed us. So both scientifically and folklore-wise, it all kind of makes sense. Halos around the moon are often taken as a sign of incoming rain. So some of you may have seen it, but if not, on the next full moon, do have a look. But sometimes when the moon is bright enough, you see a halo around the moon. Now that halo is technically known as a 22-degree halo. 22 degrees is basically the width of the halo if you measure it as an angle from the Earth's surface. That's just indicative of the distance the moon is from the Earth. But nonetheless, if the moon does have a halo around it, a lot of people see that as a sign of incoming rain. Once again, the cloud base is dropping, giving the halo, and therefore we can expect a lower cloud base with a taller cloud. Therefore, there's a good chance that we are going to have rain. Seaweed was often used in early folklore by coastal communities to predict humidity and rainfall. So if the seaweed was looking damp, that meant that the humidity was high, which meant that you were in the process of getting in some warm, wet air. Warm, wet air always means cloud and precipitation, because the warm air rises, it cools, the water condenses and falls out of the cloud as rain. So folklore played a huge part in understanding the weather. But as we got into the 1600s, we started to see weather instruments starting to be developed that allowed scientific meteorology to start to form. One of those first meteorological instruments that was used was the barometer, because people started to understand that if the pressure was low, then we did have higher wind speeds. Now, this was worked out a lot by the height of the tide. If the tide is higher, the pressure was seen as lower and the wind was expected to blow. Whereas if the tide didn't rise as high when it was expected to, then the pressure was higher and the weather would be seen as fairer. So the relationship between barometric pressure and weather was formed very, very early. And in 1643, Evangelista Torricini invented the barometer, which of course was later refined in the UK by Robert Hooke, a device for measuring pressure. But sometimes it's not the measuring of the pressure that is used to define a good forecast, it's the tendency of the pressure. And the barograph came very, very quickly, as people realised that if you could monitor the pressure and you could see the pressure falling, then you could start to forecast the weather, and therefore scientific forecasting started to become a real possibility. Jump forward to 1659 and the UK starts to record the longest running weather record in the world, the Central England Temperature Series, which is still maintained today. So that's weather records that have been kept for well over 300 years. Now, by the time we reached the 1800s, there was widespread use of thermometers and barometers both in the UK and at ships at sea, and therefore the forecasting of weather became very, very good. Now, there's forecasting in the short term and there's forecasting in the long term. Our folklore and our barometers are all short-term forecasts. We see the barometer falling, we know that in the short term there's likely to be high wind speeds. It's a bit like the red sky in the morning. We see the red sky in the morning. In the short term, we're probably going to see some wind and some rain coming. So short-term forecasting was a relatively easy thing to achieve, both in folklore and, of course, in science. A lot of the way that forecasts were derived changed in 1859 when the pivotal moment in UK forecasting history happened. And that's the steam clipper, the Royal Charter, sank off the coast of Anglesey during a very, very violent storm. And this killed a lot of people in its day. Killed 450 people went down with that ship. Of course, a tragedy of this magnitude would prompt public outcry, particularly from the maritime community, and this in turn led to the government taking action. And they decided to appoint Vice Admiral Robert Fitzroy in 1854 to form the United Kingdom's Met Office. It was initially established as part of the Board of Trade, and it initially focused on gathering meteorological observations to improve maritime safety, i.e. short-term forecasting again. Yep. Observations such as our folklore, observations such as our barometer and our thermometer are indications that are going to give us accurate short-term weather forecasting. So in 1861, Fitzroy issued the first public weather forecast in the Times newspaper, and people were able to look at what the short-term forecast was. Now, between 1861 and 1865, storm warnings started to be sent by telegraphs to ports, and Fitzroy coined the term weather forecast and developed one of the world's earliest forecasting systems using, of course, short-term barometric pressure and wind changes. Now, as we moved into the late 19th to earliest 20th century, the Met Office started to introduce what were known as synoptic charts. These were mainly analytical charts at the time, not forecast charts, that showed the distribution of pressure systems across wide areas. This enabled mariners to receive these charts initially over very, very rudimentary fax machines that basically worked upon a series of noises coming over the telegraph system, and these would print out using a revolving arm and a spark on very, very heat sensitive paper, would actually develop a copy of the synoptic chart at sea, allowing masters to start to analyse the pressure systems and make their own decisions regarding the weather forecast. The two world wars, World War I and World War II, obviously made weather a very, very important factor. During operations, amphibious landings, flights, etc., the weather became strategically important, and the ability to forecast the weather was seen as a major advantage in any wartime scenario. Radar was used, of course, during World War II, and radar was very, very good at picking up rain. So approaching rain squalls and showers were now being observed at larger distances. Weather radar, in particular the precipitation radar, is still an important key in weather forecasting today. Now, as we go into the sort of 1950s to 1960s, the Met Office moved on massively with numerical weather predictions. Now, numerical weather predictions use computers to predict what's going to happen based upon probability of something happening that has already happened in the past. In other words, historical data being used in numbers to try and predict the weather. This meant that weather could be predicted further and further in advance. And this is the crucial thing about modern weather forecasting. It's not the short-term weather. We can all look out of the window and see the grey cloud coming over the horizon. It's the long-term weather predictions, allowing ports to put in place measures very, very far out, captains to take measures on ships at sea to reduce the effect of any poor weather that is experienced. The 1960s saw the launch of the first weather satellites, which provided cloud and temperature data from space, allowing meteorologists to get a better understanding of the chaos that exists in the upper atmosphere, which drives so much of our weather and allows things like tropical revolving storms and low pressure systems over the UK to generate. The Met Office adopted global models and began using high-altitude weather balloons and jet stream analysis in the 60s as well. The jet stream is fast-moving air about 6 kilometres above the Earth's surface that drives along a lot of our weather systems. And understanding the jet stream, in particular its location, and in particular where the jet stream kinks, which is where it accelerates, gives us a much better understanding of the ability for storms to forecast very, very quickly. If a storm forecasts so quickly in the UK that the barometric pressure drops 24 millibars in 24 hours, this is known as explosive cyclogenesis and gives us a very, very intense storm, which we all need warning about. The ability to see through to that upper atmosphere and in particular identify where the jet stream was accelerating made the forecasting of these so-called weather bombs a lot more accurate. Forecasting models started to become a lot more accurate in the 1990s when the Met Office started to use supercomputers to generate forecast models. Using the data from satellites, radar, aircraft, ships and weather stations, these supercomputers were able to generate forecasting models and allow us to look way in advance. Now, even in the modern day and age, the certainty of weather forecasting deteriorates rapidly after about 48 hours. But we can still predict with some form of probabilistic certainty. I know that's a oxymoron in itself, but some form of probability what's going to happen. We can do that using data from the various weather observing stations, both on ships and ashore, pumping them into our supercomputers and getting the computer to forecast. In the present day, from the 2020s onwards, of course, AI starts to become more prevalent in forecasting. Machine learning, more powerful computers allow historical data to be used to predict. But let's bear in mind that although the focus has expanded to climate change modelling, more accurate marine forecasts, flood prediction, and aviation safety, let's bear in mind that a lot of these supercomputers use historical data. Global warming and other factors are changing weather patterns, making historical data less and less meaningful to a long-term prediction forecast. So the Met Office in itself, although it has generated a lot of data, generated a lot of expertise in being able to predict what's going to happen with the weather, Admiral Fitzroy's start was just the beginning, and his forecasting now, due to climate change, is starting to lose a little bit of its edge. Hence why we've now got these slight variations which can have big effects, as I explained earlier on, in our ship handling. Just as a matter of interest, you may be aware that recently a new weather forecasting area around the UK was named after Fitzroy. It's down there by Trafalgar and features now in every single Met Office marine forecast, the Sea Area Fitzroy. Now, does data at the end of the day the only way that our supercomputers can predict the weather? No, it's not. AI and other machine learning enables us to not just predict where our weather is going to differ from what it did, let's say, 10 years ago, but is able to predict global warming, so able to now predict the changes that our increasing global temperatures are going to have on both weather forecasting in terms of wind and systems that are coming across. We've still got, should we say, modest accuracy. Our short-term forecasts, sort of day 1 to day 2, should be accurate to somewhere between 85 and 95% using the Met Office's expertise and computers. Once we go beyond day 2, this starts to deteriorate. So by the time we've got to day 5, we're probably 70% chance of being accurate with a good modern model such as the UK Met Office. Once we get beyond day 5, it is a very, very rapid decrease in reliability as to how accurate our forecasts are going to be. So that by the time we get to 2 weeks, the forecasts become more probabilistic rather than deterministic due to the fact that the upper level chaos cannot be observed accurately until just before the weather event happens. That having been said, Storm Eowyn at the beginning of this year, one of the most intense storms seen across the UK and in particular across Ireland, was predicted 6 days in advance. So the Met Office's modelling was able to say that we were due to have this storm even before signs of the storm forming had actually been observed. So that gives you a very, very good indication on the ability now for the UK's Met Office to give us prior and early warning as to when these nasty systems are going to form and come in. Now, obviously, human interpretation and communication is massive still in meteorology, and our Met forecasters must have an excellent understanding of the science behind weather and climate before they're able to help predict the weather together with the computer and AI, not instead of or apart from. It's a combination really of models from computers and human interpretation and expertise that allows us to get very, very accurate forecasts. So at the end of the day, weather computers are based upon history for most part. Now, the history that we see on model collaboration, climate baselines, AI models, and analog methods are all based upon history. So when we go beyond day 2, we're really looking at a computer that is making a forecast based upon what happened when the current weather happened last time. Whereas real-time forecasting within the next 24 to 36 hours, isn't really based upon history. It's based upon observation. And that is where we start to see the accurate forecasts coming in. So real-time data drives most forecasts, but historical weather data is essential as a behind-the-scenes way of building, training, and validating weather models. Think of it like a weather forecast with decades and decades of experience. So a weather forecaster being able to know what happened hundreds of years ago, they're probably going to give you a very, very good guess as to what is going to happen in the very near future. But it is worth bearing in mind that just like yesterday evening, despite the fact that we can expect between 80 to 95% accuracy within 1 to 2 days forecast, that the wind speeds themselves were above that was forecast. I have found that sometimes recently weather providers do actually overestimate the wind speed. They kind of cover themselves so that if the winds are stronger than forecast, then they can normally take that into account. If the winds are less than forecasts, then obviously that's better because we've put the measures in place to deal with what we thought was going to be a higher wind speed. As last night showed, 10 knots above the forecast wind can have a very, very high impact, particularly on pilots and particularly on ports, which is why it's really necessary to maintain the experience of a set of pilots in the port who are constantly watching the weather, watching for signs around their local area that there may be a real issue. A great example is the visibility in the Solent. Now, I've been a pilot in Southampton, as many of you will know, for 25 years now. And I know that if the top of the Isle of Wight has a wedding veil over the top of it, then chances are that later on during the evening we are going to see some reduced visibility at some point in the Solent. Even if the weather forecast model doesn't specifically say it, the presence of that veil of cloud over the Isle of Wight is normally indicative of poor visibility of some description to follow, be it isolated in local areas or be it a general reduction in visibility along the south coast. Let's not forget that one of the real limitations of weather forecasting from establishments like the UK Met Office is they find it very, very difficult to take into account those local effects. And that's where the experience of local pilots, the experience of local ferry masters, and the experience of those who live and work in a certain area is invaluable when it comes to the ability to predict what's going to happen locally. You may be able to hear in the background of this podcast heavy rain falling on the roof of my office. Now, this rain, although it was forecast, was not forecast to be as heavy as it is. So even as I make this podcast, we're seeing weather conditions that are in excess of that was necessarily forecast. You can probably hear me raising my voice. You may not be able to hear the rain in the background, but trust me when I say it is incredibly heavy, and it's causing me to naturally raise my voice to get above it, even though you on this podcast are thinking, why is he shouting into the microphone? I hope you've got a better understanding now of how forecasts have developed over the years and the importance of having local knowledge when it comes to the ability to make an accurate local forecast where it matters the most. Getting an accurate forecast, reacting to the forecast, and being able to see through the forecast when perhaps it's not as accurate as we would expect it to be, is a skill that we must continue to generate throughout our seafarers as we move forward. Local knowledge will always exceed the ability for Met officers to predict the weather, and what happens in the Solent can sometimes be very different to that has been forecast broadly across the southern part of the United Kingdom by what is of course the oldest Met Office in the world, the UK's Met Office, and the legacy left by the Admiral Fitzroy. Thanks a lot, guys, for listening to the podcast. We look forward to welcoming you back on board soon. In the meantime, guys, do have a great day, and let's keep a weather eye open as to what's going to happen this winter with our storms. Have a great day, guys. Thank you.